Hi, my name is Christian Cody, and this is my MEMS 5001 optimization project proposal, rocket nozzle optimization. We live in a time where there is an ever-growing demand for access to space, whether it's to meet the needs of the military or the research needs of the science communities. There is no slowing down this demand. With companies like Boeing, Blue Origin, and SpaceX now developing the capability to provide commercial access to space, this demand will grow at an even faster rate. One of the biggest hurdles for years for spaceflight has been the cost. One way to help reduce this cost is to produce a more efficient ride to space. The idea being a more efficient rocket will use less propellant to put the same payload into space. Without reinventing major portions of the rocket, there are still things we can do to improve the efficiency of spaceflight by optimizing smaller aspects of the rocket. One of those being the design of the rocket's nozzle. A rocket engine uses its nozzle to accelerate hot exhaust gases to produce thrust, as described by Newton's third law of motion. The amount of thrust produced is dependent on the mass flow rate through the engine, the exhaust velocity of the flow, and the pressure at the exit of the nozzle. The most common type of nozzles used on rockets today is the convergent-divergent nozzle, also known as the de Laval nozzle. Shown in the image on the right, the CD nozzle converts the slow-moving, high-pressure and high-temperature gas in the combustion chamber into high-velocity gas of a lower pressure and temperature. Note that the exhaust velocity and the pressure at the exit of the nozzle are inversely proportional, so as one increases, the other decreases. The equation on the right is used to calculate the thrust force a given rocket will produce. Looking at this equation, it shows that the thrust produced is dependent on the ambient pressure surrounding the rocket. Since rockets transition through the Earth's atmosphere, they experience a wide range of ambient pressures. This makes the design of a nozzle the crucial part of the overall efficiency of the rocket, and it can be optimized to perform best in the ambient pressure it will be in the most. The interaction of the exhaust pressure and the ambient pressure plays a large part in the optimal design of a rocket nozzle. Underexpansion occurs when the exhaust pressure is higher than the ambient pressure, causing the exhaust to plume outwards as it leaves the nozzle. This results in less than optimal thrust, as some of the kinetic energy of the exhaust is wasted pushing the gas outward instead of away. It is common to see this near the end of a rocket's flight, where the ambient pressure is at its lowest. Overexpansion occurs when the ambient pressure is greater than the exhaust pressure and pushes the exhaust flow back in towards the center line of the nozzle. This also results in less than optimal thrust, and if the pressure differential becomes large enough, flow separation can occur near the nozzle walls, causing instability in the flow, which can lead to damage. The optimum interaction between the exhaust gas pressure and the ambient pressure is for them to be equal. It is here that the rocket will produce the most thrust. To find the optimum design of a nozzle for a given rocket, I plan on using MATLAB to develop a nonlinear program to maximize the specific impulse of the rocket by only influencing the shape of its nozzle. The specific impulse is a good indication of engine efficiency. The constraints will be developed from isentropic flow equations, the thrust force equation, and the compressible area ratio formula. To limit the complexity of this nonlinear program, this optimization will only address the nozzle shape and will neglect any material properties or thermal management considerations. Thank you.